Okay, so for number 33, we've got a plastic ball that's hanging from a string and it's in a uniform electric field. And we want to figure out what the charge is on the ball. And they give us the mass of the ball, they give us the angle that it's hanging from the string, and they give us the value of this uniform electric field that it's in. All right, so I'm gonna share my paper now. Right, always good to start out drawing a diagram to kind of help you visualize the problem. And what kind of a problem is this? We're looking at a ball that's in equilibrium here. How are we going to figure out the charge on the ball? We know it's hanging at a 15-degree angle. We'll call that theta. It's in a uniform electric field that points to the right, right? That means no matter where in that electric field it is, the force is going to feel the same, or the charge is going to feel the same force. And we know the value of that electric field they give to us is 1 times 10 to the 3, or 1,000 newtons per coulomb. And I think we also have the length. Do we have the length of the string there? Let me see. Go back.
It's 20 centimeters.
Okay, yeah, they do give us the length. Okay, right, 20 centimeters for the length of the string. So I'll convert that to meters, right? It'll be best to use the SI units. So 20 centimeters, 0.2 meters. And we know the mass as well, right? The mass they give us is 2 grams. And if we want to convert everything to SI units, we know that's 0.002 kilograms. And we're looking for Q, right? Our unknown is the charge on the ball. So we know that we're in equilibrium. So we know that the forces have to balance out, right, in both directions, in the vertical direction and in the horizontal direction. So that means, and you know, we're always going to want to draw basically a free body diagram anytime we're working with a problem with forces, whether they're in equilibrium or not. So what we've got here, there's well, what are the forces that are acting on the charge while it's there in equilibrium?
Gravity and tension.
One more time, one at a time.
Gravity and tension, you said.
We've got gravity, yeah. So gravity is in what direction?
Down.
Negative j hat.
Yeah, exactly. Gravity's down the negative j hat direction. That's right. I'm just going to draw it right now. It's downwards. And do we know an expression to figure out the force of gravity?
Mg.
Yeah. Force of gravity is just mg, right? And both of those are information we have, so that's good. We've got the tension, right? That's the other one. What direction should I draw the tension in?
Positive j hat.
Is the string pulling on it directly up?
Sorry. It's gonna go to the diagonal.
Yeah, it's
so
gonna
15
be
degrees.
Right? Yeah, it's gonna be like this, right? Because it's just the tension is always just along the string. So the string's pulling up on the ball in this way. You're right, at an angle of 15 degrees from the y-axis, right? And that's our tension T. Do we have an expression that we can write what that
T equals negative mg?
I'm not sure about
Actually,
that.
No, wait. That's wrong.
That is wrong. We don't know yet, right? That's something that we aren't sure yet what that force is or what the value of the tension is going to be, but hopefully we'll get there.
Okay.
And is there any other forces?
The electrical force.
There's an electrical force, right? There has to, well, we can already tell you can't be in equilibrium with this force, right? Because the tension is pulling it at least somewhat to the left. So we're in equilibrium. There has to be another force that's pulling it somewhat to the right. And that is the electrical force. right? And what direction is the electrical force? Is it purely to the right, or is it in some other direction? How do we know?
To the right.
It is going to be to the right. And how do we know the electrical force is just to the right? On the positive
The
eye?
arrows.
Yeah.
The arrows are pointing towards.
The arrows, right? The arrows are the arrows of a uniform electric field. And what those mean is that any positive charge that's placed in that field is going to feel a force in that direction, right? To the right. So the electrical force is going to be to the right. And do we have an expression that'll tell us what the magnitude is of the electrical force?
It's
One
the,
second,
the
sorry.
test charge times the electrical field.
Yes, say that one more time.
Test charge times electrical field.
Yeah, it's the charge of the test charge, or the charge of the ball that's hanging there, right? We actually have in this problem, we have an actual charge as our test charge. So that's going to be Q, right? Which is our unknown. The goal of this problem is to figure out what value this Q has, and then multiplied just by the value of the electric field. Right, so the electric force, this is just the definition of the electric field, right? A charge placed in the electric field times the value of the field gives us the electrical force. Okay? So are there any other forces that we're missing out here? Or is this?
No.
No, these are the only three forces. All right. So we know we're in equilibrium, right? That means the upwards force balances out with downwards force, leftwards force balances out with rightwards forces. And we can write down the equilibrium conditions. So let's look at the horizontal direction, right? What's the horizontal component of this tension force?
Cosine theta? Or is it sine?
Sine theta, I thought.
Theta, yeah, sine.
You're normally, right, so we got to be careful because a lot of times we'll try to make theta be the angle a vector makes with the positive x-axis, and that would make it cosine. But here our theta is just the angle it makes with the y-axis, right? So that means that the x component, well, yeah, let me write out so we know the x component of the tension is going to be the tension times the sine of 15 degrees, right? And then the y component would be the tension times the cosine of 15 degrees, right? Does everybody see why that is, or disagree with that or anything? Just drawing it out, this is Tx. And then Ty would be that component there. And I'm making that harder to see. So the equilibrium conditions is that the x component, T sine of 15 degrees, has to equal what?
Mg.
This has to equal that?
Oh, sine.
No,
Wait,
it has
no,
to equal
QE.
Has to equal Q,
Yeah, my bad.
right? That's the x component, right? So yeah, if we're in equilibrium, the x forces have to balance out. So T times sine theta has to equal our electric force, QE. And then we also have the y component. What would this similar equation look like in the y, in the vertical direction?
Now it equals T cosine.
Yeah. Well, now we have T times cosine of 15. That's the upwards force. What's that going to be equal to?
Mg.
Right. That's what's equal to mg, right? These two forces balance out. So if I take a look, right, our unknown that we need to find here is Q, right? And the only other unknown, right, I know E, I know G, I know M, I can find the sine and cosine of 15 degrees. The only other unknown is t. All right, so what should my next step be?
Solving for t.
Yeah, I can solve one of these for t and then plug it in, right? And then I should have my q. But there is a little bit of an easier way to do, right? Because I don't really care what the value of the tension is. So I can recognize that if I just, kind of like we did in a problem earlier in the week, if I just divide these equations, I'm gonna have my t cancel out. So let's see what happens if I do that. It's perfectly fine to try to solve one for t and plug it back in, but this will definitely be quicker. So if I divide my two equations here, right, I have t cancels out. What do I get if when I divide a sine by a cosine of the same angle? What's that equal to?
Tangent.
Tangent.
Yeah, tangent. So I get tangent of 15 degrees equals just QE divided by mg.
But you know what m and g is, right? So you can multiply m and g by tangent of 15.
Exactly. I can multiply mg times the tangent of 15, and then I just need to do one
And you
other.
can divide by e.
Divide by e, and that's going to give me my q, right? And then I can go ahead, and that's pretty much it, right? I just need to go ahead and plug in my mass. If I stick with the SI units, my mass is 0.002 kilograms times g, 9.81 meters per second squared.
Isn't that negative?
G
Because
is
you're going downwards?
the magnitude of g, right? Whenever you see g just by itself, that's magnitude, right? So you don't put the negative sign in there, right? The negative sign.
Oh, because you're just finding the magnitude. Okay, I see.
Right, because we're just looking at the magnitudes of the forces here because we know the downwards force balances out with the upwards force, right? So this
I see.
this positive number equals that positive number.
All right.
Times the. Yeah, go ahead.
No, never mind. I was gonna give you the answer for that, but never mind.
Yeah, we'll do it all at once.
Word.
And then we divide by the electric field, which is just 1,000 or 10 to the third newtons per coulomb. Right, so that's how we'll get our Q. So let's see, 0.002
I
times
think it's 5.25
5.25 again. It sounds good. Let me check.
times 10 to the negative.
Yeah. Yeah, so 5.25 times 10 to the minus, and I like to put it, if we can put it in scientific notation mode on the calculator, makes that easier to see. That's absolutely right. We have 5.26 times 10 to the minus 6. And what would the units here be that I've worked out here?
Coulombs.
Oh wait, never mind.
It is going to be coulombs, but we don't need to just trust that, right? If I know this is the reason why it's always good to keep your units in, right? Because you can go a long way to checking that you've done it right just by making sure the units work out. And you can definitely tell you've done it wrong if the units don't work out. But on top here, a kilogram meter per second squared, that's a common unit. What's that?
Newton.
That's Newton, right? So we've got a Newton on the top, then divided by newtons per coulomb, right? We've basically got a newtons over a newtons per coulomb. The newtons cancel out. Coulombs is in the denominator of a denominator. So we just get coulombs as our unit. All right. And that's exactly what we would expect. If we have SI units in all our inputs, we're going to expect to get the SI unit for charge in our answer. And that's what we did get. And so, and another way to write that, especially because we've had questions about converting units, right? Which SI prefix could I write this as? Which SI prefix is 10 to the minus 6?
Mu coulomb.
Yeah, micro, right? Which is the symbol mu. So really, instead of saying what we would almost certainly say, instead of 5.26 times 10 to the minus 6 coulombs, we would write, whoops, 5.26 micro coulombs. And both of those would be right. And you know, either way is fine.
Mr. Marcus.
Yeah.
So the length doesn't have any effect on the answer, does it? The length of the
No, that's a good point. The length does not have any effect on the answer, right? That didn't come into any of our equations here. So yeah, only the angle is important, but not the length.
okay.
That's a good point. That's a good thing to notice. Yeah.
There's another way to solve this question, right?
Maybe. Yeah. There's usually more than one way. What were you thinking?
Well, I was thinking of just canceling out all the forces until you got. Well, you're looking for the charge, so never mind.
Yeah,
Okay.
you do. I mean, you pretty much have to use the fact that it's an equilibrium, right? So that the upwards and the downwards forces balance out, and the left and the right balance out. Where kind of the freedom comes in is in, you know, solving these two equations, right? You don't necessarily have to divide them. You could solve one for t and plug that into the other one, and then that would be fine as well. But I think you do need to go this route and say upwards and downwards balance out, leftwards and rightwards balance out. And again, if you know, I strongly advise always weighting as, you know, some of our problems like this one do have numbers that we need to plug in. You're always going to be better off waiting as long as you can to plug any numbers in, right? I got this expression for Q just in the symbols. I could have even written this as theta still, before I went and plugged numbers in. Because then if you screw up the numbers, you can at least see your equation is right and you can go back and try again. Other questions on this problem, number 33?
Nah.